In Chapter 5, we're going to talk about the finite element method, which is quite different from the finite difference methods we've studied so far. The main advantage of the finite element method is its ability to handle more general 2- and 3-dimensional regions. In one dimension, the advantage is not so pronounced. There are actually really more than two different brands of the finite element method, two that are widely used. There's the Galerkin method, which we're going to study first, which is by far the more popular one, for reasons we'll see. The other is a collocation method, which will be first introduced in section 5.4. It's much less widely used. Let's illustrate the use of the Galerkin method on this 3D problem. Remember from chapter 0 that this transpose here can just be interpreted as a dot product. So whenever you see the del t, just think of a dot product there. There's a reason for that notation, but it was discussed in chapter 0. So this means the divergence of d times the gradient of u minus a times u plus f equals 0. So it's a fairly general 3-dimensional linear problem. On part of the boundary, u is given. On part of the boundary, the flux is given, d times the partial of u with respect to n. These are called, the first is called essential boundary conditions, Dirichlet type boundary conditions. The second are natural boundary conditions, Neumann type boundary conditions. They're handled very differently. Now, to use the Galerkin method, we first transform this strong formulation, the partial differential equation formulation, into what's called a weak formulation before we actually apply the Galerkin method to it. And here's the reasoning behind the weak formulation. According to the partial differential equation, this is equal to 0 for all points in R. Therefore, if we take that term and multiply it by any smooth function phi, we should get exactly 0. We integrate that, we get 0. On the other hand, over the natural part, the part of the boundary where natural boundary conditions, Neumann boundary conditions are given, this is satisfied. Therefore, this term in brackets is also 0 on that boundary. And so if we multiply that by phi, obviously we still get 0. So trivially, if u satisfies that this is 0 throughout region R and this is 0 on the natural boundary, then multiplying by phi, we should obviously get 0. Now at this point, we do an integration by parts, a multi-dimensional integration by parts. Remember, integration by parts is basically taking the product rule backwards. The divergence of phi times d gradient of u is equal to phi times the divergence of d gradient of u plus gradient of phi times d divergence of u. You can look in the review of multivariate calculus at the book homepage to review your multivariate calculus 3 here, but this is a standard formula from multivariate calculus. And so we replace this term here, phi times divergence of d gradient of u, by these two terms. Here's the second term. And then we apply the divergence theorem, which is basically the multidimensional analog of the fundamental theorem of calculus. It says that the integral over a region of the divergence of some vector is just equal to integral over the boundary of that vector dotted with the unit normal. And so this term here becomes this plus that. Then we still have this term, which is just copied from that. And then I forgot to mention that we're assuming phi is arbitrary and smooth, except that it satisfies phi equals 0 on the essential boundary, R1, del R1. So phi is arbitrary except that it's 0 on del R1. Therefore, this is 0 on the del R1, but not necessarily on del R2. and these two terms just cancel, and we get that. So basically from here to here is just applying the integration by parts, multi-dimensional integration by parts. So this is essentially equivalent to that. And this is called the weak formulation. Notice that there are no second derivatives of u or phi or anything here. That's very important. That's the main reason for the integration by parts. It gets rid of the second derivatives. See, here we had second derivatives because divergence of d times the gradient of u involves second derivatives of u, and in fact first derivatives of d. In the weak formulation, there are only first derivatives of u and phi and no derivatives of d. That will be important also. But the weak formulation is equivalent to the original PDE in the sense that you can go backwards and say if this holds for all smooth phi satisfying phi equals 0 on the essential boundary, then u will satisfy the original PDE and the natural boundary condition. So we're going to start from this so-called weak formulation for the Galerkin method. So we're going to assume that our approximate solution, notice we're consistent here in using capital U for our approximate solution and little u for the exact solution of the PDE. So our approximate solution is going to be written as omega plus linear combination of some phi I, where the phi I are going to be a set of linearly independent trial functions which are 0 on the essential boundary, and omega is a function which satisfies phi equals r on the essential boundary r1. So that guarantees that the essential boundary condition is automatically satisfied because this will be r on del r1, and each of these is going to be 0. Therefore u will satisfy the initial boundary condition, the essential boundary condition. We don't have to worry about that. So we plug this into our weak formulation. In other words, we plug our approximate u in for little u here, here, and here into the weak formulation. Now obviously we can't satisfy that for all smooth phi, so we simply require that this weak formulation be satisfied not for arbitrary phi, but for our phi, each of our phi k, which remember do satisfy phi k equals 0 on del r1. So here are the Galerkin equations. We've basically just plugged in capital U for little u and replaced the phi in the weak formulation by phi k. And now we have a finite number of equations, a finite number of unknowns. In fact, same number of equations as unknowns because remember the approximate solution, there are m unknowns. The phi I and the omegas are soon to be given. We're going to specify those at the beginning. We'll see what some possible choices are, but those are some known given functions. We're trying to find a1 through am, which make this satisfy the weak formulation, not for all phi. If it satisfied it for all phi, then we'd have an exact solution of the partial differential equation, but just for the phi k. So that gives us m equations and m unknowns. So we simply take our expression for u and plug it into the weak formulation, but replace general phi by phi k, and we get m equations and m unknowns. So these are the Galerkin equations. If we actually plug that in and simplify, and we take all the leave all the little a sub i's on the left hand side, we get a system of linear equations that looks like this, where the coefficients of the B vector and the coefficients of the matrix are as given here. So we're going to have to solve a linear system with matrix A, where the coefficients of the matrix A are given here, and the right hand side vector components are given by this. And once we have the solution, the little a's, then we have our approximate solution by plugging those in here. Of course, we could choose the omega and the phi I to be any functions we want which satisfy omega equal to r on the del r1 and phi I equal to 0 on del r1. But in the finite element method, we want to choose the phi I and the omega so that A is sparse. Otherwise, we have to solve a full linear system, and that's not good. So we're going to always choose the phi k such that they have small support. In other words, they're going to be piecewise polynomials, basically, which are non-zero only on a small portion of the region. Therefore, for most k and I, either phi k or phi I will be 0 at all points in the region. We'll give some examples in a minute, but that way for most k and I, aki will be 0, because in the entire region either phi k or phi I will be 0, and therefore all of these terms vanish for most ki. Now, before we go to some examples, are there any convergence theorems that can be proved easily, any error bounds that we can prove? And in fact, there is an error bound given in section 5.1, and what is shown is that the error, that is the difference between the true solution of the partial differential equation and the Galerkin solution, is less than or equal to the difference between any function in our space, any function that can be written as omega plus a linear combination of phi I minus u. In other words, that the Galerkin solution is as good as anything in the solution space in the set of trial functions, namely any function that can be written as omega plus linear combination of phi i's in the ELF norm. Now, what in the world is the ELF norm? Well, it's defined here, and it's kind of a funny, little bit unnatural norm, but it is a norm, assuming D is positive, which it will be, its diffusion coefficient, and assuming A is positive, which we have to assume. In fact, if A is negative, there's no guarantee that the partial differential equation itself has a solution. Similarly, for P has to be positive to be sure that there's a unique solution of the partial differential equation. So assuming P and A are greater than or equal to 0 and D is strictly greater than 0, this is indeed a norm. And in this funny norm, the Galerkin solution is the best of all approximates in that solution space. Now, of course, it would be nice to come up with a similar error bound using some more natural norm, such as the infinity or 2 norm. Unfortunately, that's not as easy to do. However, in practice, we can safely assume that the Galerkin solution is always going to be nearly the best, will be on, let's say, the same order as the best solution in the trial space. In 5.2, we give a specific example. We're going to take a one-dimensional problem now, and our omega and phi I functions are going to be piecewise linear functions, and we're going to define the chapeau functions, ck, to be a piecewise linear function which is 1 at its point xk and 0 at all other points. So it looks like that, looks like a little hat or tent. It's sometimes called hat or tent functions. And notice that there's the essential boundary consists of 1 point, namely x equals 0. The natural boundary consists of 1 point, namely x equals 1. And we're going to expand u as omega plus linear combination of ai phi I, and we're going to take omega to be r times c0, which is 1, or is r, rather, c0 is 1 at 0, therefore omega is r at c0, as it has to be. In other words, omega satisfies the essential boundary condition. Phi k will be ck for k equals 1 through n. Notice it does not include k equals 0, which c0 is the only one which is not 0 at x equals 0, so all of these are 0 at x equals 0, so all the phi k do satisfy they satisfy phi k of 0 equals 0, whereas omega of 0 equals r. Therefore, if U is omega plus a linear combination of the phi k, then U will be equal to R on the essential boundary, and that essential boundary condition is satisfied automatically no matter what the AKs are. Now the one-dimensional formulas for the components of the A matrix on the right-hand side are given here. Notice that A is going to be a sparse matrix because unless K is within 1 of I, then either phi k or phi I is going to be 0 at every point in the region 0, 1. Therefore, AKI will be 0 unless K and I are within 1 of each other. If I equals K, obviously this won't be 0. If I is K plus 1 or K minus 1, then it won't be 0. But if it's K plus 2 or K minus 2 or further from K, one or the other is going to be 0 at all points, so A will be sparse. In fact, as we've just seen, it'll be tridiagonal, so we actually end up with a tridiagonal matrix again. Here's our B. Now, these involve integrals. These can actually be calculated exactly because the phi k's are just linear, piecewise linear, and the phi k's are piecewise constant. However, this involves a general function R, F, and so the BKs are going to have to be calculated using some numerical method. For general F, we can't do the integration, so we're going to use the trapezoid rule, which is a very simple rule, and we get a surprise. After we calculate all the components of the matrix A, and remember for each K, only 3 of them in each equation are going to be non-zero, and we calculate formulas for the BK, we end up with exactly the finite difference equations that we derived way back in chapter 1. And since we know that these finite difference equations have truncation error delta x squared, and since they're stable, the error is going to be order delta x squared. That confirms that for this method we get delta x squared error, which is what we would expect from our error bound, because if we take W to be simply the interpolant to the exact solution, then using a standard interpolation error bound, we can show that the true solution U can be approximated by its interpolant to an accuracy of delta x squared. And remember, our working assumption is that the Galerkin solution will be as good as any function, a good approximation to the true solution as any function in the trial space, for example, an interpolant. So we typically calculate the interpolation error and assume that the Galerkin solution is just as good as an interpolant, and that's true in the F norm and say approximately true in other norms. Of course, that's a lot of work to do just to derive the standard finite difference method. Of course, most finite element methods, when we use other trial functions, we won't get standard finite difference approximations. In fact, we're going on to the next section. And in section 5.3, we're going to be using piecewise polynomials again, but piecewise cubic polynomials. In particular, we're going to be using cubic Hermite polynomials. Now, if you approximate a smooth function by piecewise polynomials of degree S, you should get accuracy delta x to the s plus 1 unless you do something stupid. So this, if we're using cubics, piecewise cubics, we should expect now to get 4th order accuracy. That is, error should be proportional to delta x to the 4th unless we do something stupid, and we're not going to. Okay, for cubic Hermites, we're going to be using trial functions which look like this or this. Now the HKs, we're going to have HKs and SKs. The HKs are piecewise cubics in each subinterval, different cubics in each subinterval, but they're chosen so that HK is equal to 0 at every point except its point, xk, and its derivative is going to be 0 at every point. On the other hand, the SKs are going to be piecewise cubics, which are 0 at all points, and its first derivative is 0 at all points except its points. And remember, a piecewise cubic has 4 unknown parameters in each subinterval. That is, in each subinterval, a cubic Hermite has the form a plus bx plus cx squared plus dx cubed. It has 4 parameters, and if you specify the value and derivative at each point, you've uniquely specified the cubic polynomial in that interval. So these definitions uniquely define elements in the cubic Hermite space. Those are the ones we're going to use for our omegas and our phi k's. Here are the actual formulas for HK and SK, but don't worry about those. Those are going to be provided for us. We know they're uniquely specified because we're specifying the value and derivatives at each of the grid points xk, and that uniquely defines a cubic in each subinterval. Now it's important to notice also that each of these functions is not only continuous but has a continuous first derivative. That's going to be very important because this cubic polynomial and this cubic polynomial have the same value here and the same derivative. Therefore, the value and the derivative are continuous. Same thing here. So they don't have continuous second derivatives, but they do have continuous first derivatives. That's going to be very important. Okay, now we're going to use the Galerkin method with these trial functions to solve this one-dimensional problem. This is a nonlinear problem that we looked at back in chapter 4. Essential boundary now consists of 2 points, 0 and pi, and there is no natural boundary. So as always, we're going to approximate our solution by omega of x plus a linear combination of the phis. Omega in this case is going to be 1/2 h0 minus 1/2 hn. Why? Because h0 is the only one of those h or s functions which is non-zero at 0, and it has a value of 1, and hn is the only one of the hk's or sk's which is non-zero at the other endpoint pi, and it's 1 there. So phi is going to satisfy the essential boundary condition at both ends. It'll be equal to 1/2 at 0, 1/2 times 1. It'll be minus 1/2 at pi, because that's minus 1/2 times 1. And the phis are going to be a mixture of s's and h's. It's going to include all the s's and h's except, notice it does not include h0 or hn. Those are the only ones that don't satisfy phi equals 0 on the boundary. And so each of these does satisfy phi equals 0 on the boundary. So our approximate solution is guaranteed to satisfy the essential boundary condition because omega satisfies the essential boundary and each of the phis is 0 on the boundary. So we have the boundary condition satisfied no matter what we choose for our a's. Now the strong formulation of the PDE is that this term here is exactly 0 at all x, so we multiply it by any phi, we're going to get 0. We do our integration by parts, which in this case is normal integration by parts because it's a one-dimensional problem, and we get our weak formulation. And as always, we say, well, we'll replace little u, the exact solution, by big U, our approximate solution, which is assumed to be omega plus linear combination of the phi j's. Plug that in for u and replace phi by phi k, and we get our m equations and m unknowns. In this case, it's a nonlinear system, and we're going to have to solve it then using Newton's method. But here is the nonlinear system. This needs to be 0 for each k. Notice that k is actually going to be 2n because there were 2n of the phis. And since we're going to be using Newton's method, we need to know the elements of the Jacobian of f. And so we calculate the partial of fk with respect to ai is this. That's obtained by simply replacing capital U by this and then taking the partial derivative with respect to ai, and we get that. So remember, this is here we have the partial of fk with respect to ai, and here we have the fk. So that gives us the components of the f vector and the components of the Jacobian matrix for use in Newton's method. Now, before we go on to look at the code, the Fortran code for actually solving this problem, which is obviously going to be considerably more complicated than the finite difference codes we've seen earlier, but not as complicated as you might think. Before we actually look at the programming of Newton's method for this system, let's talk about the error. And as usual, we assume that the Galerkin solution is as good or nearly as good as anything in the trial space. In other words, anything else of the form omega plus linear combination of the phi i's. And as usual, we take our w to be the interpolant and calculate the interpolation error and show that that's certain order. In this case, we'll show that the interpolation order, the error is of order delta x to the 4th power. That is, there is an interpolant to the true solution, which is of order delta x to the 4th, so we assume that our Galerkin solution is as good as the interpolant. So it should be also 4th order. Okay, remember Newton's method for the unknowns, which are the aj's. The a vector contains the coefficients of phi k, so we iterate using Newton's method, where each iteration we have to solve a linear system with the Jacobian matrix as the matrix and the f vectors right inside. We solve that and subtract that from the previous vector of a's and get our new approximation and iterate with that. Again, calculating the elements of the Jacobian matrix and the f vector involves some integrals. We're going to have to calculate the integrals using some numerical scheme. We tried Simpson's rule and the Gauss 3-point formula, and Simpson's rule was not accurate enough. That is, it gave us an error which was not 4th order in delta x, whereas the Gauss 3-point rule was sufficiently accurate. There are some theoretical justifications for that, but we won't go in. It's in the book, but we won't go into it in this video. The Jacobian matrix in this case, by the way, is no longer tridiagonal, but it is still banded. It has this kind of structure. Okay, now let's start to look at the code for solving this problem. Remember that omega is 1/2 h0 minus 1/2 hn, and that the phi I, there are 2n of them, are all of the s's and the h functions except h0 and hn, which are up here in the omega. In other words, basically the coefficient of h0 is known from the boundary condition, it's 1/2. The coefficient of hn is known, it's minus 1/2. So we're basically just taking the known ones out of the phis and putting them into the omegas. And so there'll be 2n phis, and they will be s's and h's in this order. That complicates things a bit, the fact that the phis are alternately s's and h's, but we'll see how we handle that. Okay, here's part of the code. What is phi sub I? Locate tells you whether it's an h or an s, and at what point it's centered. What's the k? Here's k. So it basically defines the phi i's in terms of either sk's or hk's, and then here's our omega, which remember is 1/2 h0 minus 1/2 hn. So this defines our omega, this defines the phi i's. Now this part of the code, figure 533b, is code that is going to be used for all our Galerkin problems. The user doesn't have to fool with it. Here is where the SKs and the HKs are actually defined using those formulas for the cubics. These are defined for you. You just use HERM. You pass it either in a string which is either a H or a S, and the point at which it's centered and the value of x at which you want to evaluate it. And IDER is either 0, 1, or 2 if you want the value, first derivative or second derivative, of your SK or HK. Remember, this function is given once and for all. You don't need to write that in any of the problems. And there's also given once and for all a subroutine or function which calculates integral of a given function using the Gauss 3-point formula, which we found was sufficiently accurate to not ruin the order of convergence. Now back to our nonlinear problem at hand. Remember that the components of the Elf vector were given by this integral, components of the Jacobian matrix are given by this integral, and here's where they're defined in the code, this function and this function. The Elf function defines the function which is integrated. This is exactly the integrand in the Elf sub k definition, and here's where the integrand for the Jacobian element ki is given, and that's exactly what the partial of Elf k with respect to ai was. And finally, in the main program, notice we do a maximum of 15 Newton iterations, and here we define the components of the Elf vector for Newton's method by calling our Gauss function to integrate FUN Elf, which remember was just the integrand that we need in the definition of Elf k. And then here we calculate the components of the Jacobian matrix. This is basically A of k comma I stored in band form, and we call Gauss again to integrate FUNJ, which was the integrand for the element partial of Elf k with respect to ai in the Jacobian. Then we call our band solver to solve that linear system that we have to do every step of Newton's method, and we subtract the solution. This is your delta, that's the solution of Jacobian of delta equal to Elf from A, and get the new solution. Okay, a good bit more complicated than our finite difference programs, but that can't be avoided. Results with n equal to 4, 8, and 16. If we use Simpson's rule, the error goes down by a factor of about 8 each time we double n, cut delta x in half. If we use the Gauss 3-point rule, which we will from now on, goes down by a factor of about 16, so we get our delta x to the 4th accuracy that we normally expect using piecewise cubic polynomials. Okay, in section 5.4 we're going to introduce the collocation method, and we're going to use it to solve this linear problem with these two boundary conditions. This is your essential boundary condition, this is the natural boundary condition. We're going to use the collocation method now with the what is the collocation method? Well, basically you start from the same expansion for your approximate solution. In other words, for both the collocation and Galerkin method, we assume u to be omega plus linear combination of phi i's. So for the collocation method, as for the Galerkin method, for this problem, we assume that u is omega plus linear combination of the phi's, where omega is simply 1.1 Sn. Now, why is omega equal to 1.1 Sn? Well, remember what the boundary conditions. Here are the boundary conditions. The 1.1 Sn ensures that at x equals to 1, the derivative of Sn is 1, and so you just get 1.1. So, and then at u equals 0, you can consider that the omega includes a term 0 times h0, so it satisfies both of these boundary conditions. And we'll take our phi1 through phi2n to be S0, H1, and so forth, and notice that missing that all the SKs and HKs are here except H0 is missing. It's in the omega. Actually, it has a 0 coefficient. And Sn is missing because it's in the omega. So again, we basically take take all the SKs and all the HKs, and we know the coefficient of H0, it's 0 from the boundary condition. We know the coefficient of Sn, it's 1.1 from the boundary condition. So we take those out and put them on omega, and automatically we have both boundary conditions satisfied now, no matter what the AI are, so we don't have to worry about the boundary conditions again. Okay, so far that's just like the Galerkin method. We're expanding u in the same form. The difference is, in the Galerkin method, you basically multiply by phi k and integrate to get your equations. Here it's actually simpler. We simply plug in, we simply require that the PDE itself be satisfied exactly at certain collocation points. In other words, instead of multiplying this left-hand side through by phi k and integrating from 0 to 1 and using that as our system of equations, we simply say, I want this PDE to be satisfied exactly at certain points. Obviously, it can't be satisfied at all points, as that would be infinite number of equations with only m unknowns, but we can force it to be satisfied at m points, and that's exactly what we do with the collocation method. So it's actually easier to describe. Notice that doesn't guarantee that the solution is exact at those collocation points or at any points. It just means that the PDE is satisfied at those collocation points. So for the collocation or the Galerkin method, we expand it in this form, in a form which automatically takes care of the boundary conditions. The Galerkin method, we take our u and plug it in the PDE and multiply by phi k and integrate by parts. With the collocation method, we simply plug in some collocation point zk. And for this example, these are the equations we get. Remember, u is omega plus summation of ai phi, so I've taken the omega in each term off to the right-hand side and left the ai's on the left-hand side. And as with the Galerkin method, you end up with a system of linear equations. Here's the right-hand side, here's bk, and this is aik, or aki. And again, the matrix is going to be sparse if we use same kind of phi's that we've been using. Okay, let's look at our collocation program. And again, we have to define omega, and remember it's 1.1 times Sn plus 0 times H0. And then locate, for each I, it tells us what phi I is, whether it's an H or an S, and whether the subscript, what the subscript is. So this is defined to define the phi I's in terms of the HKs and SKs. And the main program is even simpler than the Galerkin method. For each of the ZK, which we'll talk about what the ZKs are, the collocation points, but ZK are going to be the collocation points, that is, the points at which the partial differential equation has to be satisfied exactly. Here's your BK. It's exactly what the right-hand side was of the equations we looked at. And here's your A of Ki, and that is exactly the left-hand side. Compare that. This is the BK, and this is the AKI. Notice there's no integrals to calculate, so it's actually easier to program. Now, what do we use for the collocation points? Well, there are 2m unknowns, so we need 2n unknowns. M is 2n. 2m unknowns, so we need 2m equations. That means we need 2m collocation points, so we simply take 2 collocation points in each subinterval. But it turns out to be important which collocation points you take. We tried simply putting them 1/4 and 3/4 of the way through each interval, and the order turned out to be only second order, which we should expect to get fourth order. Remember, if you using cubic polynomials, even though this is not Galerkin method and we don't have any error bounds, we expect when we're approximating by piecewise cubics, we should get fourth order delta x to the 4th power accuracy, unless we do something stupid. It looks like we've done something stupid here. We used the wrong collocation points, and it turns out that you need to use the Gauss 2-point, the integration points in the Gauss 2-point formula as the collocation points in order to preserve the 4th order accuracy of the method. Now, one important difference between the Galerkin and collocation methods: remember, the Galerkin method used that weak formulation where there were no second derivatives involved. We got rid of them by the integration by parts. The collocation method does involve second derivatives. That means, for example, if we cannot use the chapeau functions, if we tried to use the hat tent functions of section 5.2 for a collocation method, it couldn't possibly work, because those all have 0 second derivatives at the integration points, at the collocation points, and these would be identically 0. However, so it turns out that the collocation method, assuming we're solving a second order problem, which we are, requires trial functions, phi's and omegas, which have continuous first derivatives. That's why we're using these cubic Hermites. They do have continuous first derivatives, and they will work. However, the piecewise linear functions do not have continuous first derivatives, and they won't work with the collocation method. They do work with the Galerkin method.